This is section 14.2, part D. And in this section, we're just going to be expanding our skills as we get a little bit of practice in calculating these circulation integrals. In example 6, I've used one of the alternative forms, f dx plus g dy. But again, as soon as I see this, I say, okay, that's a circulation integral. Oops, you can't see that. It's a circulation integral. And therefore, I know I'm going to choose to use f dot r prime dt. No matter what form they give me, I always calculate it the same way. In this case, f is the vector field x squared comma y, and c is the path consisting of these two line segments. By the way, I wanted to make it just a little more interesting, so if you would add the square on that x, I know that wasn't part of your original statement. All right, so as far as c is concerned, c goes from -1, 0 to 0, 8. And then another line segment from 0, 8 to 2, 8. So this is one of those where you can't describe the path C as just one single equation. We're going to need multiple equations. So I'm going to have to do this in two parts. I'm going to call that path A, and I'll call that path B. So for path A, that line is actually just the line y equals, and let's see here, the slope would be a rise of 8 and a run of 1, so 8x plus the y-intercept 8. So as far as r is concerned, if I use my usual trick of letting x be t, then y would be 8t plus 8. And x is t. X went from -1 to 0, so that means I'm going to be going from -1 to 0 for my t's. Oops, I said it, I just didn't write it. -1 to 0. There we go. All right, I need r prime. That's going to be 1, 8. And I also need f. This is my x, this is my y. And f is x squared comma y. So x squared will be t squared. Y is still 8t plus 8. My integral then goes from -1 to 0. F dot r prime. So here's f dotted with r prime. Which is going to be t squared plus 8 times 8t plus 8. All right, not a hard integral to do. You can do the algebra, integrate by hand, whatever. I think I just put this in the calculator just like this. I got 97/3 when I did that. All right, similarly, we'll do path B. Path B is just the horizontal line y equals 8. So for r, again, I'll let x be t, y is just 8. Since x is t, and the x's go from 0 to 2 for this part, that means the t's also go from 0 to 2. R prime will be 1, 0. And f is x squared, so that's t squared, comma y, which is 8. All right, that should be everything I need. So my integral goes 0 to 2. I take f dotted with r prime. Which is just going to give me t squared plus 0. And again, either in your head or on your calculator, that is 8/3 when we integrate. So the final answer to this is just going to be the sum of the circulations on both paths. Which gives me 105 divided by 3, or 35. All right, let's take a look at example 7. In this case, we want, once again, this is just another form for a circulation integral right here. It's one of those ones I recognize, so I'm going to do it the same way, f dot r prime dt. Our vector field is minus y, comma x, comma z. Sort of a three-dimensional rotational field. Our path C is the helix, 2 cosine t, 2 sine t, t over 2 pi. And we're going to go once around from 0 to 2 pi. Everything's pretty well set up for me with this one, but I did want to do one three-dimensional example with you, which is kind of why I threw this one in here. So, it is a circular helix. I could sketch it if we want to. Won't hurt, I guess. Let's see. Its radius is 2. So go around one time, and as I go around, I'm going up, so I end up directly above the point that I started with. So there's C. Now we know that R was given to us. Just going to jot it down here. I'm actually going to write that as 1 over 2 pi times t, just a little easier for me to work with. My interval is given right there, so I don't really have to rewrite that. The derivative r prime, negative 2 sine t, 2 cosine t, and this derivative would be 1 over 2 pi. And then for f, the r defines x, y, and in this case z as well. So plugging in here, my first component is minus y, so minus 2 sine t. My second component is x, 2 cosine t. And my third component is z, so 1 over 2 pi times t. My integral goes from 0 to 2 pi. And then I'm going to take f dot r prime. Which is going to give me 4 sine squared t plus 4 cosine squared t plus 1 over 4 pi squared times t dt. Four sine squared t plus 4 cosine squared t is just 4. Plus 1 over 4 pi squared times t dt. And once again, that one's actually not too bad, even if you work it out on your own. It comes out to 8 pi plus a half if you work it out by hand. If you do it on the calculator, it's about 25.633. All right, so there's a three-dimensional example for us. All right, we're going to take one quick look now at a quick summary of the two sort of conceptual or application areas that we've looked at with these line integrals of vector fields. And then I'm going to look at two last examples that I really like to explore a little bit again visually, geometrically, so we can sort of see what's going on. Again, our two main applications of the line integral, f dot TDS, are the work This is the work done by F. In moving an object along C. A very slight difference in interpretation. Circulation calculated the exact same way, right? No difference in the methods that we use to calculate these. The circulation just measures the amount of F. That is moving in the direction of C. Same exact calculation, almost the exact same concept. In both cases, the key is it's how much of F is in the direction along C. So whether we're asked for work or circulation, either way, we're always going to go back to this integral, which is always evaluated as F dot R prime dt. So in example 8, sees the unit circle traversed once counterclockwise, and we're asked for circulation. As soon as we see circulation, we know it's that F dot R prime dt that we're integrating again. Notice here F is our rotational field minus yx. This is somewhat similar to a problem that we've already done. Bear with me, it'll only take a couple of minutes because I'd like to compare it to part B. So, C is one time around the unit circle. Counterclockwise. That means that for R, we can just use 1 cosine t and 1 sine t. Meaning R prime will be negative sine t comma cosine t. And F is, let's see if this is my x and this is my y. F is minus y, so minus sine t comma x cosine t. And the circulation then is going to be the integral all the way around, so 0 to 2 pi of F dot R prime. Taking the dot product gives me sine squared t plus cosine squared t, or just 1. And if I integrate 1 dt, I get t, evaluated from 0 to 2 pi, which is just going to give me 2 pi. All right, let's use the same path. The unit circle traversed once counterclockwise, but this time I want the circulation in a different vector field, 0, 1 minus y squared. Notice this is going to be a completely vertical vector field. The x component is 0. The y components are the only ones that actually count, so all my vectors in this vector field will be up and down. We'll look at a picture from Maple on that in just a couple of minutes. All right. R is going to be exactly the same. I'm still looking at the path being that unit circle, which means that R prime has not changed either. But this time when I go to look at F, x is 0, and y is 1 minus y squared would be sine squared t. So my circulation integral is once again going to go 0 to 2 pi. I didn't draw it again because it's the same path of F dot product with r prime. And my dot product is going to give me a 0 here, and then a cosine t times 1 minus sine squared t. And once again, just to kind of speed things up, I did this on the calculator, and I got 0. All right, let's take a look at the geometry and see if we can figure out why those two answers make sense. Why did I get a positive circulation here, but a 0 circulation there? So here's that rotational vector field that we had in part A. F is minus yx. And remember, we were going on the path around the unit circle. That was actually true for both of them. So the unit circle, just a circle of radius 1. There we go. We were going around counterclockwise. And our calculated circulation here was 2 pi. This one, again, we've seen an example similar to this before. We want to go around the circle, and notice that we're going in the direction of the arrows. My vector field pushes me exactly the way I want to go. So I'm getting a lot of positive circulation in this calculation. If I was thinking of it as work, this vector field is doing all the work it possibly could to push me around that circle. The circulation couldn't be any better. Now, let's think about the other vector field. This one is the 0, 1 minus y squared. And we, again, are going to go around the unit circle counterclockwise. I think I used a slightly different scale here. Here's 1, negative 1. So here's my unit circle. Why would I have gotten a circulation of 0 here? Well, let's just pick a couple of points. I'm going to pick one point, for example, over here. And then I'm going to pick a similar point over here, kind of symmetric across the y-axis. What's happening over here is that, although it's not perfect, the vector field is somewhat helping me go the way I want to go, right? The arrows are pointing up, and I am going somewhat up. So I would have a positive contribution to my circulation over here. Now what about here? The arrows are still pointing up, but I'm trying to go down now. And so this would have a negative contribution. Because of the symmetry of both the vector field and the unit circle, this positive contribution and that negative contribution would have the same magnitude. So essentially, they're going to cancel one another out. Here it's helping me, here it's hurting me. The net effect is 0. If I thought of the interpretation as work, over here, the system is doing work to help me move along this curve. Here, I have to put work in to help me move along that curve. You could do that for any pair of points that are symmetric across the y-axis and see the same thing happening. All right, we are going to pause there, and we'll come back for the last example of a circulation integral in the next video.